So lesson 5 is mostly a review of integration because it's things can look very similar but then be integrated very differently just because of one small thing that's going on. Some things in lesson 5 will be new that we will be talking about in class this week. It's just these last 3 integration rules dealing with inverse trig. But every other integration rule on here we have seen before somewhere. So example one is one of the new ones. I'm going to start off by just pulling the 4 out of the integral. I'm going to write the dx on top. You don't have to. X squared plus 9. This is one of the new ones. This integral looks like number 19. I'll write a little number 19 right here. Because I could rewrite this as 4 the integral dx of x squared plus 3 squared. Or better, maybe it's even better if I rearrange this as 3 squared plus x squared. So now looking at number 19, you can see the 3 squared is like the a squared to see that a is equal to 3. And you can also see that the x squared is like the u squared to see that u is equal to x. Well, if u is equal to x, then du is equal to dx. So now I'm ready to go in and do some substitution. But you don't really have to do substitution in this case because the du and the dx worked out perfectly. But we do have 4 times the integral of du, because dx is du, 3 squared plus u squared. And u is still a. So now I'm actually using this rule here to get that I have 4 times 1 over a, which would be 1 over 3, arctan, which is tan inverse, of u over a, plus c. So my final answer, I'm getting 4/3 arctangent, or tan inverse, of x over 3 plus c for that antiderivative. So that's example 1. And now notice how example 2 looks very similar to example 1. It's just that now the 4 that's in the top has an x with it. We didn't have that before. So now that the 4 does have an x in it, we don't have to use an inverse trig rule like 18, 19, or 20. Now we can just use u sub, because if I let u be the denominator, du is 2x dx. There's lots of ways we could do this. I'm just going to multiply both sides by 2 so I can see that 2 du is 4x dx, which is exactly what I have in my numerator. So for that 4x dx, I'm subbing in a 2 du. And then in the bottom, that x squared plus 9, that is just my u. So I now have 2 times the integral of du over u. And du over u, that should be one of the rules on here. That's number 5. The integral of du over u is natural log the absolute value of u. So we have 2 natural log absolute value of u plus c. And then I'll sub back in what u is, which is x squared plus 9. Which doesn't really need absolute value because that'll always be positive, but I prefer you just write it. Especially if you don't know when you don't need it. So that's example 2. Example 3, very similar, but now both of the top and the bottom are now squared. So u sub would not work too well here. But what we can do, because the top and the bottom have the same degree, is I'm going to start off with long division first. So I'm going to be taking 4x and dividing it by x squared plus 9, or 4x squared and dividing it by x squared plus 9. I start off asking myself, what do I multiply by x squared to get 4x squared, and that is a 4. So now I'll multiply the 4 to give me a 4x squared, multiply the 4 to give me a 36, and then we are subtracting these. That cancels. I'm left with a remainder of negative 36, and the process stops there because there is no x squared down here next to that 36. So what we have just seen is that this division on the inside of the integral can be rewritten as 4 plus, well really minus, because the remainder was a negative 36. And the remainder stays over the divisor. So it's really quick, like a sidebar. We did that division. We did this division, and the answer we got was 4 minus 36. Because we got quotient over, or quotient plus remainder over divisor. So we did that division and then we replaced what we were integrating. So now I can actually come in and integrate this. I'm going to separate this into two separate integrals. And I'll pull the 36 out of the first integral. Oh, pull the 36 out of the second integral. Now the first integral is easy. That's simply just 4x. For that second integral, the dx of x squared plus 9, I'm looking at, again, rule number 19, which I'll pull a little screenshot of over. So we can see that to apply this, again, u is like x, and a is 3, because we have x squared plus 9, and 9 is 3 squared. So I'm now going to fill this out. And we don't have to worry about really doing a true sub because du is just dx. So we have 36, 1 over a, so that's 1 over 3. Arctan, I'm just going to write tan inverse. They're the same thing. U over a, so that's x over 3. And then I'll make sure to add my constant c. So our final answer is 4x minus 36 over 3 is 12. Tangent inverse of x over 3 plus c. Okay, so example 4 is a little bit different because typically, example 4, I could start this off and say that u would be this, what's under the square root, but the problem with that is then du is a negative 2x dx, and yeah, I could move the negative 2, but then I still don't have anything to do with that 3. So first I'm going to separate these into two separate integrals, so that I could deal with that 3 separately. So this is going to become the integral from 0 to 1 of x over the square root of 4 minus x squared, and then I'm going to add a separate integral from 0 to 1 with the 3 in the top. Now for that first integral, we've already talked about how we could integrate that. The first integral we can integrate using u substitution. We can let u be 4 minus x squared, and then du would be a negative 2x dx, and then I could say that negative 1/2 du is x dx, and then I could go through with my substitution. I'm also going to go ahead and change limits in this one just so I don't have to worry about switching back to x. I'm going to go ahead and switch limits from x to u. So we have old x limits of 0 and 1, and when I plug them into what u is, which is 4 minus x squared, I get out 4 and I get out 3. Just 4 minus 0 is 4, and 4 minus 1 is 3. So after substituting, my integral becomes negative 1/2. The integral from 4 to 3. And make sure that you keep the order of your limits the same. So like 0 was the lower limit, and so 4 needs to be the lower limit. 1 was the old upper limit, so 3 needs to be the new upper limit. So I have the integral from 4 to 3 of du over the square root of u. So that's really u to the negative 1/2 du. Right, that was the 1 over the square root of u. So I will increase my exponent so that my new exponent is now a positive 1/2. I will divide by it, so I'm multiplying by 2, and then I will evaluate that from 3 to 4. My 2's cancel, and I'm left with the negative 1/2, negative u to the 1/2. And I'll plug in my upper limit of 3. And then I will subtract, plugging my upper limit of 3, subtract, but we're subtracting a negative, so it turns into addition. And then I'll plug in my upper limit of 4, and the square root of 4 is 2. So I have the first integral evaluated. Whatever we get from the second integral, we will continue to add that all together to get that final answer. So I'm going to go ahead and just pull the 3 out of this integral to just leave me with dx over the square root of 4 minus x squared. One thing that will tell us that we cannot use, we can't do u sub, is if we were to let u equal 4 minus x squared, and then we would not have an x in the top that would show up in our du. So what I mean by that, 1 second, I'm trying to get this thing pasted. Okay. So what I mean by that is, you see on the left when we did u sub, there's an x that shows up in du. We were able to capture this x dx right here, but there is no x that's showing up over there, so that's not going to work. But this trig rule does work, and this is rule number 18. And this is again one of those inverse trig rules. We can see that our a squared is 4. So our a is 2, and our u is simply x, because we do have 2 squared minus x squared. So our du is just dx. When this happens, when your u is just x and your du is just dx, you don't really have to go through the substitution. You can just fill this out. So we have 3 times, I'm actually going to integrate now to get arc sine or sine inverse of u over a. So that's x over 2. And then we're going to be evaluating that from 0 to 1. So we're going to first plug in the upper limit of 1. So we have arc sine of 1/2. And then we will subtract and plug in the lower limit of 0. So we have arc sine of 0. Arc sine of 1/2, we're answering in radians here, is pi over 6. Then arc sine of 0 is 0. 3 times pi over 6 is pi over 2. So this pi over 2 that we got from this second integral up here, I'm going to add down here to the answer that we had before. Just add it right there. To get all of this down here, a positive 2, a negative 3, and a positive pi over 2 as our final answer, which you could then check this in your calculator by putting the original in your calculator, and you should get out approximately 1.839, which is what we get. Okay. So for example 5, I have the same rule number 19 posted here again. And I know that it doesn't necessarily look like it's going to be that rule because we have that x squared showing up in the numerator. But what you should be thinking when you see this is, you see this 16 minus x to the 6th. We know we can rewrite x to the 6th as something squared. So in other words, I'm saying I could rewrite this integral as x squared over the square root of 4 squared minus x cubed squared. And the only reason I'm doing this now is to explain why you should even be thinking about this rule. So I know I can do that. Look at what's under that square root, 4 squared minus x cubed squared. That doesn't look like any of the other rules, right? It looks the most like 18. 19 doesn't even have a square root, and then 20 also has this u showing up outside of the square root in the bottom, and we don't have anything else like that. But then I understand still being concerned about this x squared that shows up in the top. But once you see that your u is going to be x cubed, then you know that du is 3x squared dx. And even though we don't have that 3 there in our integral, so we will divide both sides by 3 and say 1/3 du is x squared dx. So now we see how we will account for this x squared dx when we come and do our substitution. We will be replacing that with 1/3, let me move this over, du. Now in the denominator, we still have that 4 squared right there, but then we are subtracting not just x cubed squared, but that is u. So we are subtracting u squared. And clearly a is 4, since that was a 16 and that is 4 squared. So now I can actually apply this rule. I'm going to fill this out to give me 1/3 arc sine or sine inverse. I'm just going to write sine inverse of u over a, u over a. Do we have limits? No, we don't have limits. Plus c. So I have 1/3 sine inverse of u is x cubed, a is 4, plus c, and there is our final answer. Example 6 is a little tricky because there's a very specific little thing that we have to do in order to integrate this, because the problem that we run into is that if we try to choose u with this written as it is, as what's in the denominator, we get that du is e to the x dx, which we do not have in the integral. So this does not work. But the hint that helps us integrate this is taking what we have on the inside of our integral and adding and subtracting e to the x from the numerator. So doing a 1 plus e to the x and then minus e to the x. So, and let me just put this in a different color. So we haven't changed anything in the problem. But now that we have it written like this, we can separate this into two separate integrals where I take this and kind of group that together over a 1 plus e to the x. That's in one integral. And then I will take this one. So there should be a minus sign here. That last e to the x I'm keeping in this last integral by itself. So I added and subtracted something to the numerator to give me more terms in the numerator, and then I could split this up. The first integral, 1 plus e to the x over 1 plus e to the x just cancels, and I'm just left with 1 dx, which we know just integrate down to x. But now in the second integral, I now have a good choice for u, because now I could choose u. Well, now I could do exactly what I crossed out here. Now if I let u equal 1 plus e to the x, then du is e to the x dx. So my e to the x dx is showing up as my du, so I'll go ahead in my integral and completely replace the numerator with du, and my denominator of 1 plus e to the x is simply my u value. So I have the integral of du over u. We know that 1 integrates to just x, and du over u integrates to the natural log of the absolute value of u, and then we'll add c. So we have x minus natural log the absolute value of u is 1 plus e to the x plus c. So when you're dealing with a problem where you have an e to the x in your integral, and when you first try your substitution, the problem that you run into is that you do not have another e to the x, try adding and subtracting an e to the x, and then breaking up your integral into two separate integrals. Example 7 starts off and it's not exactly sure what we should be choosing as u. There's two choices for u. Either we can choose u to be cotangent x, or we could choose u to be natural log of sine x. So for both of those choices of u, the only way we're going to know which one is a good choice for u is to see which one gives us a du that we can work with in our integral. The derivative of cotangent is negative cosecant squared, and so that's not very helpful because there is no negative cosecant squared showing up in our integral. The derivative of natural log sine, in general, the derivative of natural log of u is u prime over u. In this case, u is sine x, and u prime is, the derivative of sine is cosine x. So cosine x over sine x, that's du over u, and cosine x over sine x, and cosine x over sine x is cotangent x. So this is a good choice to use for u and du. Not so much this. So I'm going to let u be natural log of sine x, and then du is, and there's a dx missing here, du is cotangent x dx. So when I do my substitution, this integral just turns into this cotangent x dx is all du, and then this natural log of sine x, that's all u. So integrating u du, we just have to increase the exponent and divide by the new exponent, and we just end up with u squared over 2 plus c. And then I'm just going to substitute back in what u is. Yikes. So we just have natural log of sine x, all of that squared and divided by 2, and then we add c. And then our last example, example 8, tangent squared 2x. So in integrating tan squared, in fact, this probably does show up here, because we know that the derivative of secant is tan squared. No, excuse me. Sorry, I misspoke. The derivative of tangent is secant squared. The derivative of secant is secant tangent. Okay, so that's not going to show up on here, which is what the point is. We have a secant squared and a cosecant squared rule, but we don't have a tangent squared rule. So what we're going to do is we are going to apply a Pythagorean identity. There's a Pythagorean identity that says, we're most used to probably seeing that 1 plus tan squared, I'll just put theta for now, is equal to secant squared theta. So I can manipulate that rule to tell me that tan squared theta is equal to secant squared theta minus 1. So I'm going to be replacing the tangent squared on the inside of this integral with a secant squared 2x minus 1. And that's helpful because now I'll separate this into two separate integrals, but more importantly, we have a rule on how to integrate secant squared. We know that the integral of secant squared is tangent, looking at rule number 14. So I'm going to do a u substitution, and I'm going to let u be equal to 2x to then get that du is 2 dx to then get that 1/2 du is dx. So in my integral, I'm replacing this dx with a 1/2 du, and then I still have secant squared, but I don't have 2x, I just have u. And that last integral, the integral of x is just c. The integral at 1 is just x, and then I'll go ahead and add my plus c. So finishing up this integral, we have the 1/2 in front. The integral of secant squared is tan u, and then I'll keep that minus x plus c. And the last thing I'll do is I'll sub back in what u is into tangent. U is 2x. And then that gives us our final answer.